Time to jump back to chemistry class. For me, it's been a little while since chem class, but I'm guessing many of us may have lost track of some of the building blocks of the world around us. There are, in fact, even smaller particles than this, but for our purposes, the smallest unit of matter is the atom. Atoms are made up of 3 subatomic particles. Protons and neutrons concentrate in the nucleus of the atom and give it its atomic weight. So the very simplest element, hydrogen, has only a single proton, neutron, and electron, and they stack up from there. So, iron has roughly the same number of protons and electrons. However, elements can actually vary in the number of neutrons they have as what are called isotopes, which is going to be very important as we go along in understanding the age of rocks. It turns out you can estimate in the lab and calculate in the lab how long it takes for different elements to lose some of their neutrons. This is the half-life of an element and plays a really important role in calculating the age of rocks from rock samples. All those electrons whizzing around the center of that atom are really important too, because they're crucial for the formation of chemical bonds. Molecules form from chemical bonding, and for our purposes, there's kind of 2 types of bonds we really need to think about. Ionic bonds are the most common among inorganic, non-living things on Earth. This is typically metals and non-metals bonded together. You see, with a lot of these elements, they actually have an unstable amount of electrons, and essentially need to swap electrons fully, forming very tight bonds that are very hard to break apart. A classic example of this is table salt, sodium chloride, which involves sodium, a metal, and chlorine, a non-metal, bonded together. It takes temperatures of up to 800 degrees Celsius to melt a salt crystal, so incredibly high temperatures to break apart these bonds. But of course, if you dissolve it in water, the bonds break apart very easily in that solvent. We also are very familiar with covalent bonds because they're very important for living things. A classic example is table sugar. It's a crystal just like salt, but melts at very low temperatures. Because with covalent bonds, they're simply held together by sharing electrons instead of fully swapping them. Just a quick reminder, this is our periodic table of elements. These are the fundamental building blocks of all the matter around us, and they become less common the further up the periodic table you go. It turns out that the elements above iron, which is 26 on the periodic table, only form during the cataclysmic explosion of stars in supernovas, when you have all this energy ramming all of these smaller atoms together, creating these heavier elements, which is why elements like uranium and gold are actually relatively rare on Earth. By contrast, helium and hydrogen and lithium, some of the very, very light elements, are incredibly abundant in the universe. And our sun is powered by the constant nuclear fusion of hydrogen atoms blasted together, creating all this heat and energy that lights our planet. This is a pretty incredible picture. It shows what's called a Buck globule. And it's like a snapshot in time. This was actually taken 20 years ago, looking out about 600 light years away into space. And this shows the real-time formation of a current-day solar system, not too far afield from us. It's also probably what our solar system would have looked like 5.5 billion years ago as it began to form. Out in space, you have these huge dust clouds and gas clouds called nebulas. Over time, all of the little atoms in these dust clouds can begin to build up magnetic and electromagnetic, gravitational and electromagnetic attractions to each other, slowly collapsing in together until you suddenly have enough temperature and pressure in one area to have the nuclear fusion needed for a star. There's an artist's rendition of what the early process of the formation of our solar system probably looked like. You have this nebula collapsing in through this Buck globule process and kindling this early sun. And almost as soon as that sun was up and going, it began to blast out the high energy particles of the solar wind, scattering many of the heavier elements further away from it into the disk of the early solar system. Now, this is actually an interesting point. In this early solar system, it was harder to move the heavier elements, so they ended up concentrating closer into the sun. Things like the metals, for instance, glomming together in space to form the terrestrial planets, Mercury, Venus, Earth, and Mars. However, the lighter elements, things like the heliums, got blasted, and hydrogens got blasted further into space by the solar wind, ultimately cooling down and condensing together as gas giant planets much farther out in our solar system. Early Earth at this point in time probably looked something like this: a molten mass being constantly bombarded from space with all this protoplanetary stuff floating around in the sun's orbit. Some of this stuff actually still exists today as the asteroid belt and the much farther out Kuiper belt in the outer solar system, all this stuff that didn't quite end up as planets. And it cobbled together on Earth, bringing with it comets with all of their frozen ice in the form and with the water that they delivered to Earth, as well as both metals and non-metals, building up the planet that we know today. Incredibly, recent research suggests that Earth began to cool pretty quickly, at least at its surface, such that we already had a mostly solid planetary surface and liquid water oceans within as little as 400 million years from the planet's formation. 400 million years sounds like a heck of a lot of time, but as we'll discover in geological time spans, that's really not very much. All right, fun stuff. Rocks, minerals, where do they all come from and how are they all related to each other? Well, this is often a source of confusion, I find. People wonder, they hear about rocks, they hear about minerals. What's the difference exactly? I like to put it this way. Minerals are to rocks what cells are to our bodies. Rocks are basically a collection of different types of minerals. Minerals are just crystals of different types of chemical compounds and molecules, usually inorganic, so they don't contain carbon. So a classic example of this would be the mineral quartz, which is one of the 2 or 3 most common minerals on Earth. It's very common in New England. We see it all over the place. And it's one of those very common building blocks of rocks like granite. Now, there are a few different ways you can think about rocks. One is in terms of composition. And here we kind of have 2 big camps of rocks. One are the mafic rocks. This stands for magnesium and ferric. Think iron when you hear ferric, because the old Latin for iron is ferrous or ferric. And so these are rocks that are very dense, dark, and metallic, things like gabbro and basalt. If you've ever been to Hawaii or ever seen an island volcano, these are typically examples of basalt rocks, but we do have basalt on the mainland as well, just less of it. These basalt type rocks, these mafic rocks, are the most common types of rocks on other terrestrial planets in our solar system. But because we have so much water on Earth, over time on the early Earth, we began to form felsic rocks. These are things like granite and rhyolite. They tend to be lighter in color and also more buoyant. They're actually a little bit less dense than these mafic rocks. This stands for ferric, again, think iron, and silica. Silica is sort of the building block of one of the most common building blocks of rocks, a molecule formed by the bonding of silicon and oxygen together. And this, we'll see, had a really important role on our planet. So for the most part, think that continents in general are made out of more felsic rocks, whereas islands and then the bottom of the ocean are mostly made out of mafic rocks, but there's some exceptions in both cases. You can also think about rocks in terms of the different ways that they form over time instead of their composition. On Earth, the most common types of rocks are igneous. And when we think of igneous rocks that form from molten stuff, we often think of volcanic rocks. But in fact, most igneous rocks never erupt at the surface. They just kind of intrude, seep in among other solid rocks and cool in place. We also have sedimentary rocks that form from the erosion and breakdown of other rocks and then their reaccumulation and compaction into new rocks elsewhere. Although some sedimentary rocks actually form from living things. The classic examples are things like limestone, which forms out of coral reefs, and coal, which forms out of old mucky swamps with all of the living material in them. That's why that coal is so full of organic material. Additionally, we also have metamorphic rocks, which form when rocks essentially end up under intense temperature and pressure, often taking on these wavy shapes and forming new crystals and minerals within them. So they don't entirely remelt to the point where they become igneous again, but they're sort of this in-between stage where they've been superheated and reformed entirely. All right, this is a pretty complicated diagram, so we're not going to dive in here, but just to remind you, there's a lot of different ways that rocks can form, and they all sort of flow together. This is the rock cycle we like to think about in geology. It involves everything from eruptions to weathering to compaction, all of these different forces in play as all of these different rocks are forming over time. Believe it or not, as recently as 50 years ago, the idea that the continents move was considered pretty radical. The discovery of plate tectonics has pretty much upended geology. It's been the biggest breakthrough in Earth science in the last 100 years. And it came about at pretty much the same time as the moon landings. in 1969. Incredibly, it took a lot of pretty pioneering research back in the 1950s and 60s to suggest that continents were anything but immobile. As it turns out, back in the 50s, a group of scientists were out at sea in the Atlantic measuring the gravity and the magnetism of the ocean floor. They were trying to figure out how to spot Russian submarines during the Cold War, and they discovered something very strange. The rocks at the bottom of the ocean, these dense mafic rocks, as it turns out, had different types of magnetism. Some had magnetic poles facing north, some facing south. It turns out that the magnetic pole actually flips between the North and South Pole roughly every 600,000 years. And this is recorded in stripes on the bottom of the ocean floor because the oceans are in fact spreading, with new rock forming from huge volcanic mountain ranges in the center of the ocean that shove apart the continents. This dense oceanic crust is essentially a conveyor belt driven by intense convection within the mantle. The mantle is sort of the tar-like material of somewhat molten rock that makes up most of the interior of the Earth. And over time, it moves. Just like the boiling of water on the stove, it has these circulating whirls of convection that move around the plates of the surface. Over time, the dense oceanic crust gets formed at these mid-ocean ridges and then basically comes in contact with the edge of continents, which are essentially a little bit more buoyant thanks to that mostly lighter felsic rock. So the continents end up staying afloat for a very long time, while the dense rock of the oceanic crust encounters those continents, finds that it just can't win, and ends up sinking right back into the mantle and getting absorbed and melted down again. So the bottoms of the oceans are only about 200 million years old, 250 million years old, the oldest, whereas the continents in many cases are billions of years old. So this is a really critical breakthrough in our understanding of the Earth. It helps explain why so many features on the Earth's surface are where they are. As you can see in the lower left-hand side of your screen, this is a map of the plates as we currently know them. And you can see that many of the areas that are very earthquake prone or very prone to volcanoes are situated right at the edges of these plates. We have this intense grinding and slipping that can create these powerful earthquakes. Additionally, those sinking ocean crusts actually bring with them a lot of water, which helps to melt the rock above them, often forming lines of volcanoes just a little ways inland from the coast. Think Mount St. Helens, for example, out in Washington State. Now, down on the right-hand side of your screen is an image of what are called cratons. Cratons were the original continents formed on the very early Earth. These days, they're the quietest bits of the Earth, the areas with the coolest rock. It's cool in a lot of ways, but it's physically cool, so much so that you really don't have volcanoes and you really don't have earthquakes in these areas. It's very stable, old rock in these areas, where over time, small volcanic island chains, much like Hawaii or some of the small islands in the Caribbean, have gotten tacked onto the side of these continents, building them and building them and building them to the continents that we know today. Now, the interesting thing about these cratons, these very old areas of crust, they give us important insights about the formation of the Earth, and they're also often the areas with some of the most precious natural resources, at least excluding oil. A great example is that these cratons actually exist for so long that they have enough time through metamorphism of rocks to develop really new and interesting minerals. Or sometimes they just have the benefit of being around so long that they get bombarded with interesting meteorites that bring to Earth riches in terms of rare metals. A great example of this is the city of Johannesburg, one of the largest cities in Africa and the biggest city in South Africa, shown in the upper left-hand side of your screen. Johannesburg is actually built where it is because many millions of years ago, a platinum-rich asteroid came slamming to Earth there. So the city sits atop the world's largest deposit of platinum left over from this ancient meteorite impact. And that's also true of a lot of the gold on Earth. Much of it actually came from outer space and just ended up on these older bits of continent, places like Western Australia and Northern Canada that you often hear about if you ever follow mining news. For our purposes, we need to think about the geologic timescale. And it's a pretty sweeping amount of time. The incredible thing is how short of a period humans have been around relative to the planet as a whole. Fortunately for us, geology was developed mostly by people in Scotland and New England. So many of the terms in geology are in English. Big help for us, unlike biology, with all of these words in Latin. But back in the 1800s, when geology was developing, people were really big fans of ancient Greece and Rome. So many of the time periods in geology have Greek names. The very earliest time period was the Hadean, which has very few traces left on Earth today. That's when the Earth was forming and was largely molten. However, these very long stretches of time afterward, each about 2 billion years, the Archean and the Proterozoic, both have really substantial amounts of rock still left behind. Many chunks of the Earth's surface are from these two periods of time, giving us a lot of insights about what was happening on that ancient Earth. And then, of course, there's the much more recent chunk of Earth history where multicellular life, like us, became much more common in the last 650 million years, as we'll see. This is a pretty interesting picture. This is the Acasta gneiss, which is actually the oldest rock known on Earth. It's one of those wavy metamorphic rocks, and it dates to the early Archean, actually so old it's probably of Hadean age, and it's on one of those cratons up in northern Canada. Earth, during this Archean and Proterozoic era, the very, very long stretch of Earth history, in many places along the coasts probably looked something like this artist rendition. At this point in time, the moon, recently formed at this moment in time, would have been much closer in the sky, much more powerful tides from the moon's gravity. And for most of this 4 billion year period, we would have had no life at all on land and nothing but single-celled life in the ocean. However, life is pretty resourceful and seems to have arisen pretty quickly on the ancient Earth for reasons we don't entirely understand. But from very early times, life began to glom together as what are called stromatolites, shown by this artist's rendition in the foreground of the picture here. Stromatolites are these colonies of bacteria that form essentially little rocky shrubs in the shallows in warm water. And they still survive today in two areas, one in the Bahamas and one in Western Australia, as evidence of this ancient hint at multicellular life. Geologists sometimes refer to the Proterozoic, Greek for really early life or pre-life, as the boring billion. It was about 1 billion years old, and some would argue not too much happened within that time period. Let me tell you though, it was anything but boring, because during the Proterozoic, life was taking very interesting turns in the ocean. One of the really interesting things was the evolution of photosynthesis. Early bacteria figured out how to turn the sun's energy into food, essentially, much like plants do today, and began to pump out oxygen as a byproduct. They would suck up carbon dioxide dissolved in the water, split it apart, and release the oxygen from it, and use the carbon for their own energy. This began to release large amounts of oxygen into the atmosphere, even though the land at this point in time was still barren and given to intense erosion. In fact, they were, as we'll see, a little bit too successful. But all right, here's where we're at, this late Proterozoic time period. At this moment in time, what's now North America, Laurentia, the old North America, would have been situated down in the southern hemisphere and probably covered in a shallow sea. Many of the continents, as we know them today, already existed at this point, but they were much smaller than they are now and hadn't built out as much with as much crust having formed at this point in time. Now, how do we know this? This is another area where there's been some really interesting breakthroughs in geology over the last 50 years or so. During my time studying geology at UMASS-Amherst, I had a chance to get to know Dr. Lori Brown, one of the first women in geology, and also one of the first paleomagnetists. Now, what's a paleomagnetist, you might ask? Well, going back to those discoveries about the ancient orientation of the magnetic poles, geologists have figured out how to core rocks and figure out the magnetic orientation of metals within those rocks so that we can basically back calculate and figure out where the continents were oriented at different periods in the past. So there's been an increasingly large amount of evidence about where these continents were situated at these distant moments in the past. I told you all those bacteria were a little bit too successful. Well, they really were, because toward the end of the Proterozoic, there became so much oxygen in the atmosphere that the Earth actually iced over during the Snowball Earth period. Fortunately for us, volcanoes continued to erupt, pumping carbon dioxide back into the atmosphere and slowly melting that ice away. But even today, there are still piles of glacial debris left over from this ancient Snowball Earth, even in places like South Africa or Brazil that are anything but glacial these days. It's an awfully good thing those volcanoes did what they did. It was ready, the Earth was ready for boom time. And beginning about 600 million years ago, this date keeps getting pushed back with new paleontological discoveries, we began to see a big boom in life on Earth. This was the Cambrian explosion, the beginning of the Phanerozoic, the really big period of Earth history that we're living in right now, the Age of Life. And at this moment in time, early North America would be roughly astride the equator, while what's now Quincy would actually have been a small island chain still down in the southern hemisphere, but heading very quickly toward North America. At this period of time, the land was still pretty barren, except for a few enterprising bacteria, but life was going gangbusters in the ocean with multicellular life all over the place. We began to have things like trilobites, early shellfish, and some true monsters that would really keep me from going to the beach these days, like 6-foot-long sea scorpions dominating this early ocean. During this period, called the Paleozoic, we'll see that life developed very quickly, this early life period. But for our purposes, our regional geology was developing in some pretty interesting ways as well. You see, the land below us right now in Quincy, in fact, all of eastern Massachusetts, Rhode Island, Maine, and eastern Canada, as well as parts of southern Britain, northern Germany, and the Netherlands, was at this point in time a small island arc continent. Think modern-day Japan as kind of an example of this. Essentially a small continent, continental crust, but not really tacked on to any of the existing continents. And around this point in time, Apollonia came and collided with both Baltica, the proto-Europe, and Laurentia, the proto-North America. It had a very big impact with the addition of the Apollonian microcontinent and a string of other small island arcs that all sort of arrived at the same time period. It kicked off what's called an orogeny. An orogeny is geospeak for a mountain building event. It makes a lot of sense when you think about it. If you have these two landmasses meeting each other, there's really nowhere to go but up. And this began to force up a very, very tall mountain range, as tall or taller than the Himalayas are today. Over time, this mountain range has eroded away, leaving behind its little rump remnants, basically the Berkshires and Tectonics in western Massachusetts, and in fact, the Appalachians more broadly, up and down the east coast of the US. What happened to all the debris from those mountains? Well, you can actually find most of it down in southeastern Massachusetts. The coastal plain and Cape Cod, really all of that material is the eroded remnants of those mountains that's just kind of filled into the sea and into this lower lying area down in what's now the coastal plain. This gigantic mountain building event continued in 3 different phases, 3 different distinct orogenies recorded in the rocks, as life continued to evolve in really interesting ways. So after the Cambrian, we headed into periods like the Ordovician and later the Carboniferous. And during these periods of time, we began to see the development of vertebrates, just like us, in the form of bony fishes and huge amphibians that moved onto this hot, hot, hot Earth as life began to take over the land. We began to see early trees, early plants of other forms, and this very, very tropical world, just about everywhere you'd go, dominated by rich coal swamps that form much of our coal today during the Carboniferous period. However, this particular period came to a crashing halt during an era known as the Permian, which brought an end to the Paleozoic early life world. Now, we don't really know what happened during the Permian. There's a few different guesses. Some involve a big blast of radiation from outer space. Others involve simply the formation of the vast new supercontinent of Pangaea, tacking together all the continents in existence at the time. But we do know that the end Permian mass extinction was hands down the worst mass extinction in Earth history. It even wiped out close to 90% of the insects that existed at that point in time. And we all know the joke about cockroaches outliving the nuclear war. So it really, really must have been bad. One possible explanation is that the formation of this huge supercontinent actually had enough mountain ranges in place that it disrupted the flow of moisture, rapidly drying out the continents so that there was much less ability to support life on land. But that doesn't really explain the die-off in the ocean. Nonetheless, the demise of amphibians and gigantic insects and bony fish that had dominated the world before left lots of new ecological niches to fill in a new period of time called the Mesozoic. This is Greek for middle life. And think of it as the age of the dinosaurs, because that's what we really more commonly know it as. The first 100 million years of the age of dinosaurs, the Triassic, was this very dry Pangaea world. And dinosaurs managed to make the best of the circumstances. In fact, early dinosaurs, these sort of early reptiles, as shown in the lower part of your screen, developed scaly skin to hang on to their water, and even, in this crazy example, actually developed sails on their back in some cases to act as big radiators as they cross these baking hot deserts. Nonetheless, at the end of the Triassic, the supercontinent of Pangaea began to break apart because of the inexorable force of plate tectonics. And the breakup happened pretty much along the lines where many of these continents had been at before. So many of these continents sort of formed into their present shape prior to this and then split apart along those zones of weakness. The really big breaking point was the early Atlantic Ocean. And here, a huge rift valley began to form with the eruption of gloopy basalt oceanic crust that began to wedge apart these continents and spread out the Atlantic Ocean that we know today. This is continuing right as we speak with the Mid-Atlantic Ridge, which continues to wedge us apart from Europe and shove North America westward so that we're slowly consuming the Pacific crust, which gets sucked under the West Coast, dragging all that water with it and creating those chain of volcanoes that we know as the ring of fire on all sides of the Pacific, South America, North America, and Asia. Here in New England, we actually did have some rift formation. There was a small failed rift valley that's now preserved as the Pioneer Valley, where the Connecticut River flows in western Massachusetts, where many of the small mountain ranges there are actually pure basalt. They're leftover basalt eruptions from this period of time. And it probably would have looked something like the picture in the lower right-hand side of your screen, which shows the modern-day rift forming in East Africa, the famous East African Rift Valley, where a small continent is breaking off of Africa over the next 10 or 20 million years. The breakup of the supercontinent Pangaea led to very high sea levels all around the world as these continents shifted around and displaced a lot of water, forming innumerable shallow seas. As we'll see, all of these shallow seas are very important for our life today because they had a very important role to play in the formation of oil. People often joke that they're burning dinosaurs when they burn up oil and gas, but in fact, there were never enough dinosaurs to create all that oil and gas. Oil actually forms from the death of lots of little, of incountable quintillions of algae and plankton that sink into sediment and get squished so that only some of their organic remains stick around as the oil molecules, the petrochemicals that we now extract from the ground today. But as you can see, many of the areas that are rich in oil today were covered by shallow seas at this point in time. Note Venezuela, the central part of the US, like Texas, North Dakota, and then up into Alberta in Canada, most of the Middle East, North Africa, and parts of southern Russia were all covered by shallow seas at this point in time, forming much of the oil that we have today. Unfortunately for the dinosaurs, the universe had other things in store, and we all know how the story ends. About 65 million years ago, a mile-wide meteorite crashed to Earth in what's now the Gulf of Mexico. It instantly vaporized a vast coral reef, sending huge amounts of debris into the sky and blasting much of the Earth's surface with its shockwave, killing incountable millions of dinosaurs in the process. Over the next few years, all of this debris would have blocked out the sun, blocking photosynthesis for plants and starving the hungry dinosaurs out of existence. Interestingly, a young paleontologist just a couple of years ago made a career-making discovery out in Montana, which at this point in time would have been the coast of the interior seaway of Western North America. He actually found the perfectly preserved remains of a number of dinosaurs that were killed in the tsunami from this ancient impact. So he is all set for life, doing research on all those finds. Here's just a couple slides to remind us about the formation of oil going on at this period in time that, of course, plays a really important role today, both in terms of enriching many areas and in destabilizing others. The demise of the dinosaurs was, of course, a pretty big breakthrough for mammals. Mammals did exist when dinosaurs were around, but were little more than tiny little shrews living in underground burrows in terror of these reptilian giants up on the land above. But within just 10 or 15 million years of the demise of dinosaurs, mammals had filled just about every ecological niche you can think of by this era known as the Eocene. This is a time period by which we had early rhinos, elephants, whales, horses, and even early primates, our ancient ancestors, things like lemurs kicking around, as well as all sorts of mammals that didn't quite make it that we no longer have today. As you can see during this period, the world is starting to look a lot more like it does today, although some areas that are now still most rich in oil, like the Middle East, were still covered in shallow seas, and the Himalayas were only just beginning to form along with the Alps as Africa began to collide with Europe and India began to collide with Asia. Also, we would have had an Atlantic that was still much narrower than today because it had not spread as far as it has now. All of this, we dive into the age of mammals, raises the question, what was happening here in New England? Well, New England has been above sea level for a very long time, as it turns out, at least a few 100 million years. And the entirety of the era of mammals, it has been above sea level. So you would think, perhaps, that an area that's dry land would preserve things better. But in fact, all of the sediment that gets added into areas like lakes and shallow seas does a better job of burying things very quickly and preserving it as fossils later. So New England, although it certainly does have fossils, is kind of short on dinosaur fossils and mammal fossils from this period of time because so much of the land surface has been so steadily eroding. At this period of time, for the most of the era of mammals, New England would have been much warmer than today, much more like the climate of, say, Georgia, North Florida, or the Carolinas, and would have had these deep stream valleys everywhere as the land surface just eroded and eroded and eroded, sending debris out to the ocean. An example might be something like Quincy Gorge in Vermont, shown in the lower part of your screen, as one of these deep types of ravines or canyons or valleys that would have been very common at this point in time. However, a big change came about roughly 2.5 million years ago. At this period in time, as best anyone can understand, the Isthmus of Panama formed between North and South America. Prior to this, South America actually had all sorts of unusual critters, much like Australia does today because it had been isolated by itself. But we began to have a big interchange of animals between North and South America. Many South American animals lost out, and we added some interesting ones of our own, like armadillos that trekked northward into North America, as well as different camels and horses that lived in this earlier version of the continent. However, the formation of Panama completely disrupted the flow of currents between the Atlantic and Pacific, disrupting the flow of heat in the Earth, and also brought about this very cold period that we're actually still living in today, even with the much shorter run effects of climate change. So in this particular case, with the formation of Panama, we had almost immediately these gigantic ice sheets begin to form in the Arctic, advancing southward into the Midwest and Northeast, blanketing the continent for nearly 2 million years. Huge ice sheets also formed elsewhere, blanketing much of Europe, Siberia, and even small parts of South America, South Africa, and Australia in ice sheets. But the ice sheets extended much further south in North America than they tended to over in Europe because of the remaining flow of currents in the Atlantic Ocean. All of these glaciers, of course, had a really big role in changing our landscape. They filled in entire river valleys, rechanneling rivers in new directions. And even today, many outcrops of rocks still bear the scrape marks of these ancient ice sheets, which planed down the land surface and drove all sorts of new erosion like we'd never seen before. In fact, areas like Martha's Vineyard, Cape Cod, Nantucket, and Long Island are the remaining debris heaps from the furthest advance of the glaciers about 15,000 years ago, before they melted away and retreated up to the Arctic again. When that occurred 15,000 years ago, it left behind a landscape much more like the Arctic today. Braided streams, gravel, no plant life at all, and numerous windblown sand dunes. It was this harsh environment that greeted humans coming across a land bridge from Siberia. You see, with all those glaciers in place, it sucked up so much water out of the ocean that sea level was several hundred feet lower than today. So at that point in time, the coastline of New England would have been a few hundred miles further east, areas that are now, hundreds of miles out to sea past Cape Cod would have been dry land at this point in time. Native Americans arrived in this landscape, coming across one of those shallow areas from Siberia, and found a landscape that was quickly changing in the wake of the Ice Age. Within just a few thousand years, the ecosystem had transitioned to something more like the boreal forests of Canada. Big swamps, leftover ice-dammed lakes all over the place, and very boreal forest landscape with numerous pine trees, but much more hospitable to people than the one that had existed there even a few thousand years earlier. We have stone tools and remnants of these Paleo-Indians stretching back nearly 13,000 years in New England. And we know much of what we know about these early Native Americans from what are called shell bins, basically garbage heaps, like this one shown in the lower right-hand side of your screen in Plymouth, this dark area of organic material in the sand, where people chucked out all their leftover food, giving us some hints about what they were eating and how they were living. Okay, to take a detour from all that hard rock stuff for a second, what about soil? How does that fit into all this? Well, when we talk about glaciers, it's often a good time to talk about soil because the glaciers have had such a big impact in our soil here in New England. Now, I like to put it this way. Doctors and dentists both work to keep you healthy, but they rarely talk with each other. They go to different schools, and quite frankly, they're very different fields, even though they do similar things when it comes to keeping people healthy. It's kind of the same idea when it comes to geologists and soil scientists. Geology came about to find natural resources and water, whereas soil science was really to help farmers get better at producing crops. But they really look at the same thing. Soil is just sediment with more organic material mixed in with it in the form of dead animals and plant matter and things like that, and little air bubbles and water and things like that. So it's just the very top layer of sediment that's full of life and helps support life at the surface and is really important for engineering and things like that. Here in New England, we have famously poor soil because so much of it is so new. The glaciers had a big role in turning over soil and adding all sorts of newly eroded stuff in there that just hasn't broken down enough to really release many nutrients. Compare, for instance, the soil profile in the upper right-hand side of your screen. On the left side of the two, that's a typical New England soil, a thin layer of rich topsoil, and then there's this really crummy stuff below. That's mostly what's called glacial till, this sort of munge of silt and sand and clay just thrown together by the glaciers. By contrast, in the other side of the upper right-hand side of your screen, you can see the rich, dark grassland soil of a place like Iowa or Ukraine, where we do most of our big grain farming these days. You can see the contrast, of course. The Iowa one is much, much more fertile. Of course, all of this soil and our underlying rocks play a really important role for us today in terms of groundwater. Groundwater takes a lot of different forms, all ultimately restocked from rainwater, whether it's flowing through a river or falling directly on the soil. We have shallow groundwater underneath us at all times, which can be anywhere from a few feet to a few tens of feet deep. This is basically soil and sediment that's chock full of water, but there are often deeper aquifers as well that can form in the fractured granite rock of New England. So as you might imagine, the closer your groundwater is to the surface, the more easily it can get polluted. So oftentimes runoff from roadways or gas stations or factories can have a really big impact on these shallow aquifers. So depending where you live, you may be pulling from a shallow aquifer, shallow groundwater table, or you might be pulling from a deeper aquifer. Quincy is actually these days a beneficiary of the Mass Water Resources Authority reservoir system, drawing a lot of its water from the huge reservoirs of Quabbin and Wachusett in central Massachusetts, which are each fed by rivers out there and then diverted through these deep underground aqueducts on the way into Boston and Quincy. But many of the surrounding towns further out rely almost entirely on groundwater to get their drinking water. All right, back to our Native American friends. At this point in time, as they headed through the process of seeing New England transform into a world more like ours, began to develop agriculture and advanced clay working to form clay pots beginning around 3,000 years ago. Archaeologists refer to this as the Woodland Period, and it's sort of the most advanced period in Native American history in New England, where people would have been trading for resources as far away as Washington State, developing advanced tools and carrying out both farming and hunting and gathering. However, the arrival of Europeans in the 1600s with the diseases they brought with them brought with a severe impact for Native Americans in New England, who were marginalized beyond that point and really shunted aside by European settlement from about the mid-1600s onward. And whereas Native Americans did do some mining for stone tools, we began to see with European settlement much more significant human impacts on the environment and on geology in the region. A classic example of this is the clay pits of places like Somerville and probably also Quincy, where early settlers began to dig up clay in these shallows, baking it into bricks to build places like the city of Boston. We also find thousands and thousands of miles of stone walls all over New England, originally used to hem in sheep. These are often found out in woods that seem like they could be quite old, but in fact, our forests have mostly filled in the last 50 to 100 years, with New England almost entirely deforested before that, much like a place like Ireland still is today. Engineers and geologists and workers also did major shifts of the landscape in other ways. For instance, digging up gigantic sand and gravel hills left over by the glaciers and transporting that material by train to fill in the marshes of the Back Bay and the South End, which is why those two parts of Boston are so flat today. Beginning around the early 1800s, Massachusetts also became one of the world's leading centers of industry, along with parts of England and Britain, England and Belgium, rather. And this brought about a significant amount of pollution. There were really no environmental laws to speak of until the 1970s. So for the preceding 150 plus years, New England factories, which were as productive as anything you might find in China today, did churn out a huge amount of heavy metals and toxins, which really occupies a lot of the people that study geology in New England today, cleaning all of those up. Environmental remediation with soils and groundwater and even some deeper rocks that have amassed these pollutants is really sort of a key focus these days for people that study geology in the region. All right, the really fun part. We get to figure out the geology of Quincy. And here we're going to take a look at the bedrock geology of Massachusetts. Now remember, the sediments and soils over top of this are different, but this is the bedrock below it all. Here in New England, we actually have very shallow depth to bedrock at some places. Some people's foundations practically touch bedrock, and many of the rocks that we see at the surface are actually outcrops, where they're actually just bits of the bedrock poking through the surface. Elsewhere, we have large boulders that were often broken off or shifted around by glaciers, which sort of just sit on the surface and aren't actually attached to the rest of the bedrock. Looking at this map, you can see in the westernmost part of the state, this interesting swirl of different rocks out there. That is the old shoreline of Laurentia, the ancient North America, the really, really old one, before we tacked on that small continent of Avalonia. In fact, even today, in the city of Adams, Massachusetts, there is a big quarry digging into marble, the metamorphosed remains of the limestone of the coral reef that was right along the coast there that got squished with the arrival of this smaller continent. That is actually dug up and used to make tums. Tums are actually just crushed marble from Western Mass that get ground up for the tablets you find at the pharmacy. And as you can see, the rest of the state heading eastward from that old shoreline tends to be these sort of north-south stripes for the most part. Many of those are igneous and metamorphic rocks that are basically these kind of belts of metamorphic rock that would have formed with the compression of all these different little island chains together against the ancient North American continent some 400 or 500 million years ago. Here in Eastern Mass, we're atop the old rocks of the Avalonian continent. So in fact, Quincy's geology actually predates that of Massachusetts as a whole and was originally an entirely separate continent. There's a couple of ways to kind of break this down. You can think about this in terms of big groupings, and you can think about it in terms of specific rocks. This is really looking at some of the structural geology, the different big units of rocks that make up the region. And as you can see, a big chunk of Quincy is what's called a pluton. A pluton is a very large intrusion of granite over the size of an entire city in this particular case that would have intruded into rocks and then cooled in place and had those rocks above it slowly erode away, leaving behind this essentially big granite dome that we're living on today. And much of North Quincy and some of the islands out into the Boston Harbor Islands are the Boston Basin, which is a big low-lying area that filled in with sedimentary rocks on that ancient Avalonian continent. As we can see, there are also a number of mostly inactive faults all around the Boston area that sort of divvy up these big units. Some of these do have small shifts along them, but they tend to not be powerful enough to really cause earthquakes on their own, unlike some of the powerful, famous faults of California. This is another way of looking at Quincy. It shows some of the different rock units. And as you can see, we have the big Quincy pluton with all of that huge mass of granite rock that underlies a very large part of the city, and with those sedimentary rocks more to the north and into Boston. Classic example of the sedimentary rocks is the pudding stone, which you'll often see along I-93. That's that really cobbly, it really sort of looks like a fruitcake, the rock along there. And that was a rock that formed in this basin from the bringing together of all sorts of pebbles that all sort of eroded and amassed and compressed together. And we can see that to the east of Quincy, and even in probably some small parts of the southern part of the city, there's other large extents of granite that are beneath what's now southeastern Massachusetts and extend off to the eastward. Of course, Quincy and granite really do go together. Many people, many watching today, probably have been to the Quincy quarries, which have gotten quite a bit safer and no less interesting over time. The Quincy quarries are actually very interesting because they're an example of a huge old quarry into this pluton used to supply much of the granite used for building the city of Boston. Of course, if you look on the top of your screen, you can see the Boston skyline there. And today, the Quincy quarries are a really popular spot for rock climbing. Up until the 1990s, the quarry had actually flooded and was about 400 feet deep in points. This picture shown on the lower right-hand side of your screen is what it might have looked like in the Quincy quarries. This is actually a view from a big similar quarry in Wales in the UK. And it was a very risky place during the 70s and 80s when it was all flooded with water because people were dumping cars and unfortunately murder victims and all sorts of things in there. So it was a real mess and a real hazard to public safety. So over time, the state actually filled it in, just left all that stuff in there, drained out the water and filled it on in. But the Quincy quarries is also very important because it had the very first railroad in America, way back in 1825, still preserved today with its little incline for moving these big slabs of granite to then bring by wagon or by boat into Boston. So we've come full circle. We've told the 4 billion year story in quite a brief way, but I hope we've found out a little bit more about Quincy and the ground below us. And now I will switch over to some questions and we can go and look through the slideshow, depending on what those questions are. So I will go ahead and encourage you to put your questions in the chat, or if you'd like, you can go off mute and ask me that way.
So we did have a question as to what environmental remediation efforts are going on here now, if there are any. You had mentioned them earlier.
Yeah, I'll actually go back to my slide touching on that. I can't speak exactly to what's happening in Quincy right now, but a few of the big things for environmental remediation at the moment are things like heavy metals, lead and arsenic and things like that, that are very persistent. They stick around for a long time because they're elements. They're really hard to get rid of. There's also often problems around man-made chemicals like PCBs, which is short for polychlorinated biphenyls. I'm probably going to mess that up. I always do. But they're an example of a very hazardous and persistent organic chemical that can actually stick around from different industrial processes, as well as things like benzene from gas stations. So a lot of environmental remediation people check in on gas stations very often because if gas leaks from a gas station, it can really mess up the soil and water in the area. So there's a lot of work around that sort of stuff, depending where you are. And there's lots of different ways that geologists and engineers carry out remediation. So many people don't realize this, but if something is super polluted and you can't stabilize it in place, what will often happen is they'll bring in heavy construction equipment and literally dig up all that soil and bring it away by truck and take it to a concrete plant and put it into the kiln where they make the concrete, because at the 4,000 degree temperatures used for baking the cement for concrete, it either destroys the organic molecules or creates cement that then seals that stuff away as man-made rock in the form of concrete. So a lot of pollutants actually end up going to concrete plants to be tucked away for the future.
Oh, very interesting. I had no idea. And then I also had a question from earlier when you were talking about the different types of soil throughout the state. Someone wanted to know if what are the intended impacts of climate change on the soil?
Yeah, that's a great question. So there's probably many more in-depth studies on this. This is definitely an evolving area where geologists and soil scientists are spending a lot of time thinking about this. Here, there probably wouldn't be immediate impacts on soil. Really any big impacts would be on areas that either get wetter or drier. a really big thing. There are certain types of soils called hydrosols, like water, that are basically waterlogged all the time. They're pretty yucky to deal with. You don't really want to play around with them, but they're very important because they do host all sorts of water for different aquifers and all kinds of interesting microbes in swamps and things like that. So when different areas end up dried out or adding water, we can have the formation or loss of some of these histosols, rather, is what I meant to say, over time, which can have an important environmental impact one way or the other.
And we're not really a crop growing area, so like you had said earlier, the impact wouldn't be as great. For that reason.
What was that?
For that reason, the impact would be less on soil?
Yeah, and it would take a lot of heating up and a lot of drying out, or real big changes in moisture to really substantially change many of our soils here in New England.
Okay.
Let me just open the chat. Let's do this.
So CT had asked if he had missed anything about the giant boulders at Muswesset Hammock in North Quincy and how they got there.
Well, I can't speak to the exact specifics. It's possible I'll be wrong about this, but my guess and the explanation for most of the big boulders we find is actually the glaciers. The glaciers were capable of ripping off huge chunks of rock and transporting it in the ice and sort of just dumping it there when the ice eventually melted. So a lot of the huge boulders, even some that are the size of houses, were originally moved by the glaciers. Roma and Dirk ask, so where might Quincy be in 1 million, 100 million, or 1 billion years? Also a really interesting question. So 1 million years from now is really, in geological terms, not very long at all. So probably basically where it is now, a few inches further west as we continue to wedge apart from Europe. But within about 100 million to 200 million years, there are some proposals looking at where the continents are heading now that we may reform the ancient supercontinent of Pangaea with a new Pangaea, with all the continents tacked together. So if that's the case, we'll probably be butting up against Africa again, or perhaps fronting on a big inland sea in the middle of this continent, depending which way the continents end up shifting. 1 billion years from now is probably anybody's guess, because it's hard to tell exactly where things are going to be at with plate tectonics. But certainly by then, we'd be living on a planet much, much different than the one we have now. So we might want some space colonies by then. Anne asks, we live in an area that was called the Norfolk Downs, a kind of wetland. How was this formed? So many of the wetlands we have today, and actually it's a good thing I'm on this particular slide about aquifers and groundwater and all that stuff, many of the wetlands we have, particularly the inland ones, are low-lying areas, often sort of hollows in the rock or little fracture zones in the rock that have filled in over time with clay. Clay is one of the kind of 3 types of particles that you find in soil. And clay is actually pretty special because it's stuff that has eroded so much and weathered so much over time that it has formed entirely new minerals just through the process of breaking down. So clay is actually kind of unusual because, unlike silt or sand, the tiny, tiny microscopic surfaces of clay are actually a little bit negatively charged. So they tend to glom on pollutants onto them, but they also stick together very, very tightly, so that clay is often one of the best ways to stop the flow of water. Many swamps actually have a layer of clay underneath them, prevents them from draining well, because clay is just such a good block for water. So many swamp areas are areas that have built up clay over time and then kind of backed up water as a result of it. Donna asks, where is the most geologically interesting part of the state to you? Donna, that's a really tough question. There's some pretty incredible rocks here in New England. I have to say I'm a big fan of the Quincy Quarries. I think that's a pretty cool place to check out. But there's some pretty interesting stuff elsewhere too. Western Mass, for instance, has some very interesting minerals up in the mountains. And I always enjoy hiking the Holyoke Range, which is that east-west 7-mile mountain range that cuts across the Pioneer Valley, which was actually one of these basalt eruptions way back when, during the formation of that ancient rift valley that almost but didn't quite become the Atlantic. That's now the Pioneer Valley out in Western Mass. So it's fun to go check out that mountain range and check out the views off of it. Les asks, could you mention the ancient sea here in Quincy containing trilobites? Yeah, absolutely. So we have a lot of really interesting, so by the way, for anyone who is not very filled in on paleontology, a trilobite was one of the most common types of life on Earth way, way back 200 to 400 million years ago. They're basically like horseshoe crabs without tails. Think about it that way. They were some of the most common life in the oceans and the shallow seas and things like that. And they did not make it past that Permian mass extinction we heard about. They were one of those many types of life that just didn't make the cut. And so we have tons and tons of them in the fossil record, but none of them left around today, unlike the horseshoe crabs, which are a little bit more clever and managed to stick around. So Quincy, back during the Paleozoic, would have been covered by a shallow sea at different points in time during the arrival of that ancient continent against North America. And so we have found a number of trilobite fossils in the eastern part of Massachusetts that hint at our contact with other now very distant parts of the world, with trilobite fossils that match up with parts of what's now North Africa today, because we were so close together at that point in time with the formation of Pangaea.
So someone asked, oh, no, that's the same question. They asked about the Braintree trilobite on Facebook. So I think that's all the questions that I'm seeing online, and Kate, unless anyone else has any here they want to ask before we finish up. This has certainly been a very informative presentation. I think you covered a tremendous amount of ground here.
4 billion years worth, to be
Yes.
to be frank. Well, everyone, thank you so much for joining this evening. I hope you had fun with the talk, and be sure to get out, enjoy the beautiful weather, and check out the ground below you. Take care. Have a great night.